In this video, we'll look at how to sketch polynomial functions if they're in factored form. So in order to do this, we're going to go all the way back to when you were learning about quadratic functions, and we're going to talk about sketching this quadratic function. So it's it is quadratic, but you can see that there are two factors here. So it's in factored form, x minus 1 and x plus 2. So what we're going to do is we're going to graph this. And in order to graph this, I'll just remind you of finding the zeros. So in order to find the zeros of this function, we set the y value equal to 0. We want to figure out where does this function cross the y-axis. So y is 0 there. So we get that 0 equals x minus 1 times x plus 2. And you may not remember what it was called, but there's the zero product property. Basically, it says that if we get an answer of 0 when we multiply two things together, then one or both of those two things has to equal 0. So what that means is that either our factor of x minus 1 has to equal 0, or our factor of x plus 2 has to be equal to 0 for us to get a 0 over here. And now we can solve these equations and see that x has to equal 1, or x has to equal negative 2. And so we can sketch this now on our graph. We know that x is equal to 1, that's right here as our x-intercept, and x equals negative 2. We know that this is a parabola. We know that it opens up because it has an a value that's positive. So we have a good sense of what it looks like. If we weren't sure which direction it opens because we've forgotten, one of the things that we can do that's helpful here is to find the y-intercept. And remember, in order to find the y-intercept, we set x equal to 0 and solve for y, or in this case, f at x. So f at x, sorry, let's backtrack here. We're going to set x equal to 0. So f at 0 is equal to, we'll sub in a 0 everywhere we see an x, 0 minus 1 times 0 plus 2. Which will give us negative 1 times a positive 2, which will be a negative 2. So we know that when x is 0, y is negative 2. That's right here. So we know this is a parabola. This isn't the vertex, obviously, but we obviously know which way it opens just based on that. So we know the parabola is going to go something like this. And if we really wanted to dig into finding the vertex, we could. But for the work that we're going to do today, we're really just interested in figuring out what the general shape is. So that would be a good sketch of what this polynomial looks like. We're going to take this one step further, try to build on this a little bit. So here's one that's way more complicated, or at least looks like it's way more complicated. This is a quartic function, and I can tell it's a quartic function because it has 1, 2, 3, 4 factors. If we were to expand this all out, we'd have an x to the 4. But it is fully factored, and so we can go about this the same way that we did for the quadratic example. So again, we can set the function equal to 0. We'll do it. Some of you will be able to take a shortcut here to find the x-intercept. So we've got x minus 1 as a factor, x plus 1 as a factor, and x minus 4 as a factor, but it happens twice. And again, using that zero product property, we know that if all of these things are multiplied together and give us 0, then each of those factors has to equal 0. So x minus 1 equals 0, x plus 1 equals 0, and x minus 4 also has to equal 0. Solving each of these, we get x equals 1, x equals negative 1, and x equals 4. And so those are the x-intercepts. We're going to plot those. Maybe I'll just label that just so we remember. So we'll plot those on our grid. X equals 1 is over here. X equals, whoops, sorry, I got that backwards. That's x equals negative 1. Here's x equals 1, and here's x equals 4. So we have the x-intercepts. We could also find the y-intercept the same way that we did before by substituting a 0 in for x. So let's evaluate p at 0. So all we're going to do here, sub a 0 in everywhere we see an x. And 0 minus 1 is negative 1. 0 plus 1 is positive 1. And I forgot a squared here. Negative 4 squared gives us 16. Negative 1 times positive 1 times 16 will give us negative 16. So we know that there is a y-intercept down here somewhere. We know that the function goes through this point, so it's going to look something like this. We'll just kind of trace that in for now. We'll come back and make it look a little bit neater later on because it has to go through these points. We don't really have a good sense of what it looks like beyond that, though. So let's just backtrack here a bit. One of the things that we can do, a couple of things that we can do, is we want to test this function right here. We want to test it out for values kind of to the left of our leftmost intercept and to the right of our rightmost intercept. That will give us some indication of what the end behavior of this function is. So we're going to substitute values that are to the left of the leftmost intercept. I'm going to choose -2 because it's there. It doesn't have to be -2. It could be -3, -4, any number that's to the left of our last intercept, which is at x equals -1. So let's try p at -2. So substitute a -2 in here for all of the x values. And away we go. So -2 take away 1 is -3. -2 plus 1 will be -1. And here we'll have -6 squared. Now, the actual value here isn't that important to us. What's most important is the sign of this function. And so we know that we're going to get 3 times 36. That's a fairly big positive number, which means that our function is going to be somewhere way up here, and which means it's going to have to come down like this through our y-intercept and come back up here. So we tested the end behavior at the beyond the leftmost x-intercept. Let's test beyond the rightmost x-intercept to see what's going to happen over there. And in order to do that, let's choose a point that's bigger than 4. 5 seems like a good one. We can choose any point. I like to choose the small numbers because the math tends to be a little bit easier. So let's find p at 5. Again, we're just taking our function, p of x, and we're subbing 5 in for all of these x's. So whoops, 5 minus 1 times, that's a minus, 5 plus 1, and 5 minus 4 squared. 5 minus 1 is 4, 5 plus 1 is 6, and 5 minus 4 squared is 1 squared, which is just going to be 1. So here we'll get 24. Again, the number's not so critical here. The fact is that this is a positive number and it's a fairly large number, so this function's obviously going to do something like this and head from here on up. And the last thing that we would do is we would test in between the x-intercepts. So I don't know what's happening between 1 and 4, so I'm going to choose a value. Again, it could be any value in here. It could be 2, it could be 3, it could be 2.5, it could be pi if you really wanted to go to town with this. Doesn't really matter which one you choose here. I'm going to choose a nice easy one, p at 2. So let's do 2 minus 1. And again, I'm just subbing that into the original function, p of x. Everywhere there's an x, I'm replacing it with a 2. And 2 minus 4 squared. All right, 2 minus 1 is 1. 2 plus 1 is 3. And 2 minus 4 is -2, but that's going to be squared. So -2 squared is 4. 4 times 3 is 12 times 1. And again, it's not so much the number that matters, it's more the sign. What did we say this was? A positive 12? So we know that when x is 2, y is going to be 12. So this thing does something like this. And one of the things that you may notice here, kind of interesting, is that the graph goes through all of the x-intercepts, with the exception of this one. At this intercept, the graph just touches the x-axis and turns around and heads the other way. And you'll notice that that is this factor here. And you may notice something a little bit different about that factor. And it's this squared. So when a factor is squared, you get that sort of touch and turn kind of behavior where the graph will come down, touch the x-intercept, and turn around and head off in the opposite direction. All right. So that's, in a nutshell, is how to graph polynomial functions if they are in factored form. If a function is not in factored form, you could factor it, and then once it's factored, you could proceed here. So here are the steps that we just followed. So in order to sketch a factored polynomial, we can find we found the x-intercept or the roots or the zeros first. Doesn't matter which order you find the intercepts in, but you can find the y-intercept, find the x-intercept, test the end behavior, so that's to the left of the leftmost root, the right of the rightmost root, test in between all the roots to get a sense of what the graph looks like there, and then complete your rough sketch. So that's how we can graph polynomial functions if they are in factored form.